Okay, so now we're going to get into the physiology of blood flow. This is part 2. We're going to look at the factors that affect blood flow. Blood flow is determined by two factors, the pressure of the blood and the resistance of the blood vessels. So we have to look at aspects of pressure and resistance to determine flow. Now, flow is what we're really after. If the blood's not flowing, then a person's going to die. So the point is to keep the blood flowing and to manage the pressure and the resistance to flow to keep it flowing adequately. So when we talk about pressure, it's really difference in pressure that matters, because blood will flow from high pressure to low pressure. All fluids flow from high pressure to low pressure, and we use the delta sign, which is the Greek letter D for difference. So the delta P is our difference in pressure, and the higher the delta P, that is, the greater the difference between the high pressure end and the low pressure end, the greater the flow. Resistance is any factor that impedes flow, and resistance is actually pretty complicated to measure, so we're not actually going to calculate resistance. We're just going to see what factors affect resistance. So here's our sort of little formula. And that little sideways 8 means proportionate to. So flow is proportional to delta P over R, which means the higher the delta P, the higher the flow. They're directly proportional. The higher the resistance, the lower the flow. They are inversely proportional. So an increase in delta P increases flow, but an increase in resistance decreases flow. All right, we'll start with pressure. Pressure has to be measured at two ends of a path. So you can say the path from the beginning of the brachial artery down to your digital arteries. Or you can say the pressure of the entire systemic circulation from the beginning of the aorta all the way through to the opening into the right atrium. Whatever your beginning and end points are, you have to know what the pressure is. So as an example, for body-wide flow, the pressure in the aorta is the mean arterial pressure, which runs around 93 millimeters of mercury if you have a default normal pressure of 120 over 80. And at the right atrium, the pressure is pretty close to 0. So you have a delta P of 93 minus 0, or 93 is your delta P. If your systemic arterial pressure goes up due to exercise, that right atrial pressure always stays pretty close to 0. So whatever your systemic mean arterial pressure is, that's going to be the delta P for body-wide flow. So we're going to round it off to about 100 millimeters of mercury, and of course it fluctuates depending on your exercise. Atrial pressure, nearly 0, and even if you're exercising vigorously, it's not going to change much unless you have something like congestive heart failure. And if you have congestion, that is blood sitting in the heart and the heart's too weak to pump it out, your atrial pressure can go up, and that's going to reduce the delta P, and that will reduce flow. And of course, that can be life-threatening in situations like that. All right, arterial flow is pulsatile. You know you have a pulse. When that blood flows out of the arterioles into the capillaries, the pulse disappears, but because precapillary sphincters can open and close, capillary flow stops and starts. So if we actually looked at this, and we have some video footage of, it's in your chapter summary, some video footage of blood flowing through arterioles and capillaries and venules, you can see that because different capillaries are flowing into the veins, venous flow is pretty much constant. The next major point is that pressure must drop continuously from artery to capillary to vein. Remember that blood flows from high pressure to low pressure. So if the pressure ever reversed and went up in a vein to higher than a capillary, then the blood flow would try to reverse, and that would not be good. The greatest pressure drop is in the arterioles. Those are called the resistance vessels because they're going to drop the pressure so that it's not too high to burst your capillaries. The second greatest drop is in the capillaries because you actually lose fluid in the capillaries. Not all the fluid that leaks out of capillaries leaks back in, so you have a loss of blood volume in capillaries. Here's the diagram. So you can see the pulsatile flow, the diastolic and systolic pressure being marked. Where they have the line for mean blood pressure, that's not really correctly calculated. You learned in lab the actual formula for calculating mean arterial pressure, and you know it's closer to the diastolic line than it is to the systolic line. Notice that the segment marked arterioles, where arterioles start, you still have a pulse, but the pulse disappears, looks like about halfway through the arterioles. And then also notice the mean pressure at the beginning of the arterioles is still pretty high, about 80 or so, but by the time you get to the end of the arterioles, it's dropped to maybe 35 or 40. So it's dropped by more than 50%. And then in the capillaries, it drops from about 30 to about 15. So again, that's another big drop. In the veins, in the venous system, the pressure is always very low. It starts at about maybe 15 and drops to 0 by the time it gets to the vena cava. You might not think blood is flowing if there's 0 pressure. It's really just very low. It doesn't hit 0 until you get all the way back to the aorta. All right, now let's talk about resistance. We're going to use R for resistance. If you increase resistance, flow decreases, but if there's more resistance, the pressure increases. And so there's this confounding factor of increasing the pressure, which we know increases the flow, but increasing resistance decreases the flow, and so we've got to look at the differential effects of those. Now, there is central resistance. That's the resistance within the heart, but that's incorporated into calculating cardiac output, so we're going to ignore that for now. We're just looking at peripheral resistance, the resistance within the vessels. There are 3 factors that affect resistance. One is viscosity, vessel length, and vessel diameter. Viscosity is going to affect overall resistance. The more viscous the blood, the harder it is to push it. So that would affect central resistance as well as peripheral resistance. Blood viscosity, though, is pretty well fixed. The viscosity of the blood is based on a couple of things, and the biggest factor there is the hematocrit, the number of red cells, and that's something that's kind of fixed. You can't just reduce the number of red cells just to reduce viscosity and put less workload on the heart. So viscosity of the blood is somewhere around 4 to 5 times, and that measurement is based on a comparison to plain water. So blood is about 4 or 5 times as viscous as water, meaning it has that much more resistance to flow. There are factors in the plasma that increase resistance. The plasma proteins, our colloidal proteins, increase resistance, but their effect is minimal compared to the effect of red blood cells. So if you have a patient with polycythemia, too high a red blood cell count, the viscosity can increase to the point where it's putting a strain on the heart. It's too much work on the heart to pump that extra thick blood. On the other hand, if you have a patient with anemia, their blood viscosity is lower, and it does actually reduce the resistance, which makes it easier for the heart to pump it, but then you're not getting enough oxygen to the tissues because you don't have a high enough red blood cell count. So viscosity in the short term, viscosity is not going to change just to increase the flow of blood. Viscosity is a fixed factor that you just have to work around. The second factor is vessel length. The longer a vessel, the more resistance it has, and so we see much lower resistance in children than we do in adults. Tall people more than short people. Obese people have higher resistance, and that tends to increase their blood pressure. So this is one of the main reasons that obesity is correlated with high blood pressure. It's because the extra vessels required to feed all those fat deposits increase the overall vessel length in the body. Now, again, that's something that doesn't change short term. So if an obese person is encouraged to lose weight because their blood pressure is too high, when they lose that excess adipose, they actually see an atrophy in the blood vessels that are supplying that adipose. They have shorter total vessel length, less resistance, and their resting blood pressure can go down. Now, there is a way to temporarily shorten vessel length very quickly, and that's by closing off entire capillary beds. But you can't do that forever because all living tissue needs blood supply. So changing vessel length is not something you're going to do long term just to affect resistance to flow and to manage blood pressure. So that leaves us with vessel diameter, and that's the one thing that you can alter quickly to change your peripheral resistance, and that's vasoconstriction, which is going to increase peripheral resistance, and vasodilation, which is going to decrease peripheral resistance. Now, keep in mind that anytime you vasoconstrict, you also increase the pressure within the vessel that you're constricting. And when you vasodilate, you reduce the pressure within the vessel that you're dilating. So you're going to affect blood flow through that vessel. But if you, say, vasoconstrict broadly your entire systemic arteries, then you're going to boost the pressure enough overall that you're going to increase flow more than that change in resistance is going to decrease flow. Typically, what you're going to do is vasoconstrict some vessels while dilating others. So if you just ate a big meal, you're going to dilate the vessels that supply your digestive organs. And correspondingly, you're going to typically constrict the blood flow to your skeletal muscles to compensate for needing more blood to flow to your digestive system. So this idea of vasoconstricting and vasodilating tends to be regulated on an organ-by-organ basis. And so when you constrict some, you dilate others, and that increases the overall circulation. So it increases blood flow, but it increases blood flow to specific body parts. So when you're physically active, you dilate the blood vessels to your skeletal muscles that you're actively using, and you constrict the vessels to, say, your kidneys and your digestive organs. All right, here's a term you need to know, and it gets confusing sometimes because we're going to use some terms that sound alike in different ways. Vasomotion is that change in vessel diameter to increase or decrease peripheral resistance. And we refer to the the nerves that do that as the vasomotor nerves, and the part of the brain that controls vasomotion is the vasomotor center. Primarily, this is going to affect systemic blood pressure. We're not going to be doing it too much to the pulmonary system. Your pulmonary system really can't withstand a very high blood pressure because then you'd have fluid leaking out into your lungs. That would not be good. The greatest impact on systemic blood pressure is on the medium and small arteries and arterioles. If you want to impact specific capillary beds, you're going to hit their arterioles, and their first branch is called the metarterioles. So when we combine the effects of pressure and resistance, we see that while pressure drops continuously, resistance rises and falls depending on the diameter of the vessels. Velocity, which is the speed at which the blood is moving, is going to fall as blood flows from the aorta and the elastic arteries to the muscular arteries to the arterioles. Remember, those are your high resistance vessels, and they put so much resistance on the blood that the flow drops tremendously as blood flows through arterioles. And then blood moves its slowest through the capillaries. As blood leaves the capillaries and goes into the venules, the diameter is greater, resistance is lower, and blood flow picks up because you have a lot of capillaries flowing into the same venules. Imagine that you were on a river raft. You're taking a rafting trip, and so as you're riding your raft through a narrow gorge, you're going pretty fast. If you open up into a lake or just a wider riverbed, you're going to slow down. And then as that water flows back into a narrow channel, your velocity is going to increase again. So blood moves quickly to arrive at the capillaries, slows down as it flows through the capillaries, and then speeds back up in the veins. And this should make sense because the capillary is where the nutrient and waste exchange is going to occur. So it has to flow slowly enough through capillaries to get that job done, even when you're highly active. So a typical resting value for blood flow through a typical capillary, it takes it about a second to travel from the artery end of the capillary to the venous end of the capillary. Typical capillary is about 1 millimeter long, so you're moving at about 1 millimeter per second. And then if you speed up your activity, you can have the blood flowing about 4 times as fast, and the blood's going to flow through that capillary in about 1/4 of a second. And it's still going to manage to drop off nutrients and pick up wastes. All right, so here's just a couple of pictures. This is a completely dilated artery. You can see the black oblong objects. Those are the red blood cells. And you have the layers of the vessel wall labeled for you. And let's compare that to a completely constricted artery. And you can see the folds in the tunica intima where the endothelial layer just kind of wrinkles up. And the wall itself gets much thicker and much rounder. Okay, so we're going to talk about regulating pressure and flow. We'll do that in part 3.